Welcome to fourth and final lecture series on retaining walls. I am Vaishak C, Assistant Professor, Civil Engineering Department, Engineering College, Chalabad. So, in this lecture, we are going to continue with the design and detailing portion of the problem already discussed in the previous lecture. It is important that you see the previous lecture before continuing with this video. So, in the previous lecture, it was already seen that the initial proportion which was proposed was satisfying all the stability conditions, and the dimension was accepted as the final proportion. And also we have found out what is the active earth pressure diagram, what are the different weight components, as well as the what is the net soil pressure distribution at the base of the base slab. So in this lecture we'll start with designing and detailing of each of these elements: toe, heel and stem. So before continuing with designing, it is important for you to note that each of the elements, toe, heel and stem, is to be designed as a cantilever slab subjected to varying load. Okay, so here you can see that the toe slab is subjected to a net upward force, which means that the toe slab bends upward and it is supported in this common junction. So since the beam bends upward, toe slab bends upward, you can see that the tension side is on the bottom side and hence the reinforcement is given in the bottom face. On the other side, the heel slab, the net downward force is more, hence the heel slab bends downward. So you can see that the tension side is on the top side and hence the tension reinforcement is provided on the top in heel slab. When you come to the stem, the load on the stem is actually the active earth pressure diagram. So you can see that the stem slab will deflect to the left, which means that the tension side is on the right of the stem. In that case, we provide the tensile reinforcement at the right side of the stem. Now let's start with the design of toe slab. So this design is very basic design of a one-way cantilever slab. So we have to find out the bending moment, design bending moment, as well as the design shear force. So first let's find out what is the loading on the toe slab. So from this diagram we can interpolate the value at this portion. So here it is 142.4, which is Q max, and you can interpolate what is the value of Q at this position corresponding to the beginning of the toe slab. Also, this toe slab is made out of concrete and is having a depth of 0.62 meters, which means that it exerts a pressure of weight of 15.5 kN per meter square. That self-weight is already calculated here. So that means that there is an upward and a downward force acting. So there is a net upward force of this much acting on the toe slab. It is to be noted that the weight of the soil in the toe slab is neglected. Okay, so this is the load acting on the toe slab. It is a uniformly varying load. Now we have to assume a clear cover of 75 mm because it is below soil, and usually in structures such as footing we use a minimum cover of 75 mm. Okay, let's assume that we are going to use 16 mm diameter bars. In that case we can calculate the effective depth, which is total depth minus clear cover minus the half the diameter of the bar. It is 16 by 2, so we get effective depth as 537 millimeters. We have to apply a load factor of 1.5 while calculating the design shear as well as the design moment. One more important thing to be noted here is that the critical section for toe slab in shear is at a distance d distance away from the face of the support. This is because of the inclined crack which develops because of the support transverse compression offered by the support from the stem. So this stem is offering a compression force, transverse compression, hence the crack propagates in the toe slab in 45-degree angle. Hence the critical section is taken at d distance away from the face of the support. So now with that we'll find what is the value of Vu. So Vu is actually the area of this trapezium. Okay. Next is we have to find out mu. Mu is also 1.5 is the factored load. Load factor, and it has to be multiplied with the. So this trapezium is now divided into two parts, a triangle and a rectangle. So we find the area of the triangle multiplied by L by distance by 2, and area of the triangle multiplied by the d by 3, 2 by 3 d. Okay, so we get a value of mu as well. Once we get the value of design shear, we can also find out the nominal shear stress TV, which is Vu by Bd. So this can be found out and kept aside. So once we have the value of mu, all we need to find out is we have to find out AST, or area of steel required. So we can use the basic formula mu is equal to 0.875 AST into d minus 0.416 XU. Substituting the value of XU, we can get the final equation for finding out mu is equal to 0.875 AST into d minus Fi into AST divided by FCKB. So here the only unknown is AST. Substituting all the values, we get a quadratic equation in AST, and you can solve for finding AST, and then you can find out the value of PT as 100 AST by PD. Alternately, you can also use R value to find out PT required. So here we use this method, and we find out that PT percentage of steel required is 0.15 percentage. Okay, and from the percentage of steel required, you can calculate the AST required, which is PT into BD, 1000 into 537. It is important to note that wherever B is there, the value will be 1000, because we are designing a slab, and hence we are designing it for a 1 meter strip. Okay, so once we have the PT value, you can also find out the design shear strength value of the concrete toe C as proposed by clause 40.2.1 and table 19. Whenever PT is less than 0.15, the toe C value is 0.28. Here the toe C value 0.28 is greater than the toe V value, nominal shear 0.236. This implies that the given reinforcement is adequate in shear. So once we got the AST required, we can now find out the spacing in the slab as given in this formula. So 100 into area of 1 bar divided by AST required. So we get spacing as 249 millimeters. So we have to give a spacing of 240 center to center when we are using 16.5 bars. So the toe reinforcement will go like this at the base of the toe slab. It is important to note that we should not stop immediately at the support. It should be extended for a little length, which is called as development length, LD. So LD is actually 47 times the diameter of the bar, which means 752 millimeters. Since the beam is short, we don't talk about any curtailment requirements. Next, we will see the design of heel slab. The design of heel slab is very similar to that of the toe slab. The only difference is that there in the loading part. So here if you see, the total load on the heel side is actually the weight of the slab, okay, which is made out of concrete, it is at 25 into 0.62 because 25 is the unit weight of the concrete, and along with that we have the overburden pressure from the soil, which is having a height of around 7.75 minus 0.62, and its unit weight is 16, unit weight of soil. So the total downward force acting is 12.9 kN per meter square uniform from starting to the end, and there is a net upward reaction, upward soil pressure acting. This is Q minimum value, and this can be interpolated and found out here. And once we have a downward force and upward force, we can find out the net force, and we got the net force to be a downward uniformly varying load. Okay. Another thing, important thing to note here is that in this case the critical shear phase section lies on the face of the support itself, because there is no underlying member to give a transverse compression force. So the cracking occurs at the face of the support only. So in that case we can find out the VU and MU value as we did it in the previous example. Okay, the clear cover is also going to be the same, and D is also going to be the same. Once we have the VU value, we can find out tau V value, nominal shear stress, and keep it aside. Once we have the MU value, you can find out the A, PT, and then once you have PT value, you can find out the tau C value as well as the AST required. So compare the tau C value with the tau V value. Here also it is seen that the shear reinforcement provided is adequate in shear. So once we have the AST, you can find out the spacing of bars using 16M5 bars as assumed. So spacing is going to be 187 mm is the calculated value, so we provide 180 mm center to center. So important thing to note here is that the tension phase is on the top side, hence we give the reinforcement in the top phase. Also, it should not finish at exactly at the face of the support, it should be continuous little longer because of the requirement of development length LD. So LD is actually 47 times the diameter of the bar used. Okay, so this is very similar to the previous one. Next we will see a vertical design of vertical stem. So here we have to first calculate the height of the vertical stem, which is obvious, it is 5.25 minus 0.62, where 0.62 was the thickness of the base slab. Okay, now in this case of stem, it is above the soil, hence we can reduce the clear cover to 50 millimeters, and we assume that we use 25 bars, 20 mm diameter bars. So calculate the diameter effective depth at the base. Total depth 650 minus 50 clear cover minus D by 2, diameter of the bar by 2 is 20 by 2, so we get effective depth as 590. Here also the load factor used for both the moments and shear is going to be 1.5, which is according to LSM. Okay, now what is the load on stem is nothing but the active earth pressure. So at the top we have this value is nothing but Ca into Ws, and at the bottom it is nothing but Ca into Ws plus Ca into gamma into H, where H is the height of the stem. So here also we have a trapezoidal loading, so we can find out, calculate the value of mu at the base section. Okay, by dividing the loading into two parts, triangle and a rectangle. And here also when we talk about shear, the critical section is at a D distance away from the face of the support. This is because the toe slab exerts a transverse compression which causes a diagonal cracking on the stem. Okay, so here also the critical section is taken at D distance away from the face of the support, so we can calculate the shear force as given in the equation. Okay, once we get the shear force, we can calculate the nominal shear value and compare it with the tau c value. Okay, once we have the mu value, you can calculate AST required and PT required. Once you have the AST required value, you can calculate the spacing. So here we started with the assumption of 20 mm bars. However, we see that the total reinforcement required is very less, so we try to use the 16.5 bars only. So when we use 16.5 bars, the spacing is 115 millimeters, which means that we will provide 16.5 bars at 110 center to center distance. So this is actually the vertical reinforcement which is to be provided on the inner side of the stem. Okay, here also the effective development length is actually LD, which is 47 into 12. But the important thing to note here is that the stem reinforcement will continue all the way into the shear key, so the development length criteria will be obviously met. Okay, another thing design is actually temperature and shrinkage reinforcement. So important thing to note is that the more temperature and shrinkage crack would be happening in the phase which is subjected to the temperature changes and weathering. So the outer phase is given 2/3 of the total temperature distribution, and inner side is given the 1/3 of the total temperature distribution. Okay, so this temperature and shrinkage reinforcements are nothing but these horizontal bars shown here as dotted lines, as dots. Okay, so as per clause 26.5.2.1, the distribution reinforcement to be provided against shrinkage and temperature is minimum reinforcement, which is 12% of total area. So we have already decided that we are going to provide only 2/3 on the front facing side and 1/3 in the back facing side. So on the front facing side, we have 2/3 of 0.12% of total area, which is 615 which means that AST required on the front face is 520 millimeter bar. If we are using 8 mm bars, we get a spacing of 97, which means that we provide the reinforcement at 100 millimeter spacing at the inner side, and in the outer side we provide the reinforcement at 200 millimeter per center to center. Okay, so these horizontal bars, which are denoted as dots, are actually the temperature or shrinkage reinforcements. Okay, so whatever spacing is on the left side, the double spacing will be there on the right side, because here it is 2/3 and here it is half of that, 1/3. Okay, so it is important to note that in stem bar we do curtailment, and we do it in 2 stages. Okay, so we divide the stem into 3 equal parts, and once we divide it into 3 equal parts, in the bottommost part full reinforcement is given, which means that the vertical main flexural bars which were 16.5 bars at 110 center to center, when we come to the second portion, the space 1 bar is removed, alternate 1 bar is removed, which means that the spacing increases by double. Okay, when we come to the topmost portion, here where the bending moment is very less, so the requirement of reinforcement is also very less there. So there the spacing increases 3 times, because in between we remove 2 bars. Okay, so spacing increase 3 times. The same thing is done for temperature reinforcements also. Here we have a smaller spacing, which is 8 mm bars at 200 centimeter. Then we go to the second middle portion where the temperature reinforcements are at a higher spacing, which is 400 millimeters center to center, and in the topmost portion the temperature reinforcements are given at a spacing of 600 center to center. The same thing happens in the left side also. Okay, so you can also note that the main reinforcement from the stem continues the whole way into the shear key. Okay, the distribution bar in heel slab and toe slab is nominal bars, which shows 10 mm bars at 300 mm center to center. The distribution bar here is these dots developed, denoted, the bars denoted by these dots. That's it. Thank you for your patient listening. I hope this lecture series was useful for you. Thank you.